Welcome to Experiment 7 this week. This week we'll be doing double displacement reactions in the lab. Double displacement reactions are also called aka exchange reactions. C 9.1. We talked about exchange reactions in lecture this week. Exchange and double displacement are the same thing, so you have seen them before. So what I want to do first is just go through the lab manual pages for exercise 7 and show you what you're going to need to do, and then I'll give you some resources and discussion so that you can complete the experiment. So you're going to be evaluating double displacement reactions in this entire experiment. The thing that I want to point out to you now, and I'm going to give you some background on it in a second, is that double displacement reactions only occur when you make a precipitate or something that's molecular, such as a water or a gas. If you don't make a precipitate, water, or a gas, no reaction occurs. And so in this exercise, in this experiment, you'll be asked to figure out if a water, gas, or a precipitate is forming in order to predict these reactions. And then you're going to comment on this thing called driving force for the reaction. Driving force is just the thing that propels the reaction forward. It makes it go in the forward direction. The driving force is going to be the formation of water, gas, or a precipitate. That's what you're going to look for in terms of driving force. So I'll talk more about that stuff in just a second, but let's talk about what you need to do. In the first video that I'm going to have you watch, the one that's based on the experimental procedure, somebody from Folsom Lake College goes through and does all of these reactions from table 1, performs all the reactions, and all you have to do is write the observations for what you see. She very clearly goes through and says in test tube 1 she mixes sodium chloride and silver nitrate, and then shows it, and you just have to write down what you see. She does that for each one. You just have to record your observations. The section where you're going to need a little more background knowledge, I think, is in table 2, writing equations for double displacement reactions and these things called total ionic and net ionic equations, which we haven't really talked much about. We were going to talk about them in this lab, so that's okay that we haven't covered in the lecture. So right now, I'm going to go through and do a little discussion of what you're going to need to know in order to complete table 2 of experiment 7. So in experiment 7, you are going to be writing total ionic and net ionic equations for double displacement reactions that include acid-base reactions, precipitation reactions, and gas evolution reactions. In other words, all of these types of reactions are called double displacements. Double displacement, or from lecture, exchange reactions. So what I want to do now is go through and talk about each one of these reactions and how you know what kind of reaction it is, so that you can then predict them. All right. So precipitation reactions, they are reactions that occur when you mix 2 aqueous solutions and you make a solid. And they might look something kind of like what's going on here. You combine potassium iodide, lead nitrate, and then you make some kind of solid. In this case, what the example is showing you is you make lead iodide as a yellow solid. It's a nice cloudy solid, kind of like the solid you formed when you made silver chloride in experiment 6. So precipitation reactions are those that form solids. Precipitation is just the word we use for solid formation. The key to predicting precipitation reactions and knowing if you're looking at a precipitation reaction is that you have to be able to tell if compounds and the products are soluble or not. Only insoluble compounds are going to form precipitates. So what you're going to end up doing is predicting the reaction when you mix two reagents, and then you're going to ask, are the products soluble or not? If they're insoluble, you're going to be dealing with some kind of precipitation reaction. Precipitation reactions occur when you have two solutions containing soluble compounds. Down here, the two solutions are potassium iodide, which is soluble, and lead nitrate, which is also soluble. A precipitation reaction occurs when you mix those two soluble things and an insoluble compound precipitates are formed. So in this example, you mixed potassium iodide and lead nitrate, and you made lead iodide, which is insoluble, which is a solid. All right, and it kind of looks like this. So before you mix anything, you've got your two solutions. You've got potassium iodide and you got lead nitrate sitting around. In each of those solutions, you've got just ions. That is what this aqueous means. When you look at Ki aqueous, it means that those ions are just sitting in water. They're dissolved. They're soluble. So before you mix anything, you have Ki aqueous. It's potassium and iodine. When you have lead nitrate sitting in solution, you've got nitrate ions, and you've got lead 2+ ions. As soon as you combine them together, what you end up with is a mixture of all 4 ions. So here we've taken the potassium iodide solution, mixed it with our lead nitrate, and we get something where you've got a solution of iodide ion, nitrate ion, potassium, and lead 2+ ion, all floating around in solution. Now what's going to happen is as soon as you mix these and all 4 ions are present, the ions will swap partners. They'll pair up with the opposite ion. So you look at your original compounds, you had Ki and lead nitrate, right? That lead is going to pair up with the iodide to give you lead 2 iodide. The potassium is going to pair up with the nitrate to give you potassium nitrate. At this point, you don't know if you have a precipitation reaction. All you know is that you've made some potentially insoluble compounds, right? So you do your ion switching, you've got some potentially insoluble compounds. The next thing that you do, though, is check your solubility rules. So if the potentially insoluble compounds, products, are both soluble, we say no reaction occurs. If one or both of them are insoluble, we say a precipitation reaction occurs. To know whether they're soluble or not, you've got to use your solubility rules. So let's check this out. You mixed your original things, potassium iodide and lead nitrate. You made potassium nitrate and you made lead 2 iodide. Consult your solubility table, which is your rules, right, for solubility, and you see that lead iodide is a solid. It's insoluble. Potassium nitrate is an aqueous compound. Things that are aqueous are soluble. Means that they're soluble. So you go through, you check your products to see if they're soluble or not. If you find one that's insoluble, like lead iodide, you say that you have a precipitation reaction. And overall, it looks like this. You mix potassium iodide, lead nitrate, and you get lead iodide solid. That's this yellowish solid at the bottom. Potassium nitrate stays dissolved in solution. So In that second table for experiment 7, what you're going to be looking for is if you form when you swap partners in the reaction, right? And you predict the products, you're going to be looking for whether or not you have soluble or insoluble compounds. All right. So let's talk about how we write these reactions. Looking at how you predict a precipitation reaction. Let's look at sodium carbonate and copper chloride. What we want to do is just swap out the ion pairs. So one suggestion I'm going to give you is you need the charges to balance in the product. So what you can do is write the ions that exist in the starting materials. So sodium is sodium plus, carbonate is CO2 2 minus, copper is copper 2 plus, chloride's going to be minus, right? Once you've done that, you can just swap them. So sodium was originally paired with carbonate, which is the negative ion. Now it's going to pair with chloride, right? Copper is going to pair then with carbonate. And so you get NaCl plus copper carbonate, right? CuCO3, copper carbonate. Now what you got to do is make sure that this balances, right? So you say you got 2 sodium, you got to put a 2 in front of sodium chloride, and then I think that's it, right? Everything else balances otherwise. So once you've done that, you've written the equation, you balanced everything, you got to check to see if those compounds, those products, sodium chloride and copper carbonate, are soluble or not. Sodium chloride, checking your solubility rules, is soluble. Copper carbonate is insoluble. It's going to be a solid. As a consequence, you would say this is a precipitation reaction. So what point 4 here is saying is that if everything is soluble, you don't have any reaction. If you've got some things that are soluble, then you've got a precipitation reaction. So our overall equation ends up being sodium carbonate, copper chloride going to copper carbonate, and then 2 NaCl. Where now we've indicated what the states are on our products, right? We know copper carbonate is a solid. Okay, real quickly, I just wanted to show you what it looks like when you have no reaction. So imagine if you mix potassium iodide and sodium chloride, you've got no reaction. The reason for that is when you swap the ion pairs and you make potassium iodide and sodium iodide, these are your potentially soluble compounds. You see that potassium chloride is soluble, and you see that sodium iodide is also soluble. Because potassium chloride and sodium iodide are soluble, you would say, Ki aqueous plus NaCl aqueous gives you no reaction. So in table 2, as you go through experiment 7, look for some reactions that might not actually occur, where there might not actually be a reaction. It's going to be instances where you don't form any kind of solid, gas, or liquid. All right, let's talk about acid-base reactions. We're going to talk more in chapter 10 about acid-base reactions, but we'll cover just the most salient features of them right now so that you can do the experiment. So an acid-base reaction is going to be one that results in the formation of water. You're going to get water as a product, and then some ionic compound that we call a salt. All of the ionic compounds that we've looked at are called salts. When you do an acid-base reaction, you make a salt and you make water. So that's what you're gonna want to look for. For example, hydrochloric acid, HCl, reacts with sodium hydroxide. It gives you water and a salt. Notice what's going on is that the H from the acid, from HCl, pairs up with that OH from the base to give you water and NaCl. That's all that happens in an acid-base reaction. Bases, all you got to know to identify a base is if it has a hydroxide in it. Here's some common acids and bases. We saw these when we talked about nomenclature, but hydrochloric acid, hydrobromic, nitric, sulfuric, perchloric, and acetic are all some really common ones that you see. Common bases, notice they are all hydroxide. They're all hydroxide bases. So be on the lookout for hydroxide containing compounds when you're working through experiment 7, table 2. All right, lastly, let's talk about gas evolution reactions, and then I'm going to go through some examples. So gas evolution reactions are just going to be anything that produces a gas. They're important to know because if you make a gas, you're making a molecular compound, and you have a reaction that occurs. So if in experiment 7, table 2, you predict a gas forms, it's going to be important to indicate that. Some common starting materials that will form gases include sulfides, carbonates and bicarbonates, sulfites and bisulfites, and ammonium. Why this is important is because the reactant type helps to tell if you'll form a gas. So what you're going to want to do is look through the starting materials in your table 2. If any of them are sulfides, carbonates, sulfites, ammonium, that's going to be an indication that you might be forming some kind of gas in the product. For instance, if you have hydrochloric acid and potassium carbonate, what you predict is water, CO2, and KCl that would form. That would form in the reaction. All right, let's talk about the last thing you're going to need to be able to do besides identifying these reaction types, and it's writing these total ionic and net ionic equations. So there's 3 different types of equations that we're going to be looking at. The first one is just the balanced equation, which is called the molecular in some instances, but it's just the balanced equation that you write. Then you're going to be writing total ionic and net ionic equations. Molecular equations or balanced equation just shows everything that's involved in the equation. All of the reactants and all of the products. So silver nitrate reacting with sodium chloride to give you silver chloride and sodium nitrate. Shows you everything. It also shows you the states of matter, right? Aqueous or solid. Total ionic equations are going to show you all of the compounds that dissociate into ions in solution. So you look at silver nitrate. Silver nitrate would break up into silver ion, nitrate ion. Sodium chloride, it's soluble. It breaks up into sodium and chloride. Solids do not break up. So solids, notice silver chloride stays silver chloride. Sodium nitrate is soluble, so it breaks up into sodium ion and nitrate ion. So really important, when you write total ionic equations, you want to separate only the aqueous ionic compounds, which in this case are the silver nitrate, sodium chloride, and sodium nitrate, and leave any solids, liquids, or gases as intact chemical structures. All right, so once you get your total ionic equation, this is the same equation as what you saw on the previous slide. you're going to have these things called spectator ions. Spectator ions are ions that show up unchanged on both sides of the equation. So notice in your starting materials, nitrate and sodium also show up in the products. Sodium and nitrate. That's important because in order to get to a net ionic equation, you're going to have to know what your spectator ions are. So identify the spectator ions in your net ionic equations. Once you do that, once you notice your spectator ions, what you're going to do is cross them out. Cross them out because they don't participate in the reaction. We're going to see that net ionic equations only indicate the ions that participate in the reaction to form product. Spectator ions don't, and so you cross them out. So to go from your total ionic equation to ultimately some kind of net ionic equation, you want to cross out everything that shows up twice. So nitrate, sodium, and sodium, right? And then all you have left is silver chloride and silver chloride in the products. This resulting equation, after you've crossed out all the spectator ions, is what we call the net ionic equation. It is the net of what has occurred in the reaction. It's the starting material ions that are participating in the reaction to form product. So if you take your total ionic equation, cross out spectators, and rewrite it, you get your net ionic equation. All right, so just in summary, your molecular or balanced equations are going to reflect everything in the equation. Complete or total ionic equations are only going to show the ions that dissociate. Remember, you don't separate solids, you don't separate liquids or gases. And then the net ionic equation is the equation that shows up at the very end, only reflecting the ions that have participated in the reaction and any product, be it solid, liquid, or gas, that forms. All right, so I wanted to go through some examples here to give you a sense for how to do these things. So we're going to write the total ionic, net ionic equations for each of these following reactions. There's 4 of them here. And then also state the driving force. Remember, driving force is just if a solid forms, gas forms, or if water forms. So let's do this first one. The first thing you want to do is write out the molecular or balanced equation. So silver nitrate and copper chloride are going to make silver chloride plus copper nitrate, NO3 and then we want to balance it, right? So we want to say, there are 2 AgCl and then 2 silver nitrate. So you go ahead and balance it, and then you want to look at your solubility rules to see if any of these are soluble. Looking at your solubility rules, you see that silver chloride is an insoluble compound. Copper nitrate, on the other hand, stays soluble, so it's aqueous. So this is your balanced equation. In table 2, you're going to have to predict products like this, predict these balanced equations. Let's write out the total ionic equation next. Remember, to write the total ionic equation out, we have to separate out into ions anything that's soluble. So you look at silver nitrate. Silver nitrate's going to be broken into 2Ag+. You want to retain the coefficients from the balanced equation. So that 2Ag+ comes from the fact that you've got 2Ag. So 2Ag+ aqueous plus 2 nitrates, NO3- aqueous, plus You look at copper chloride soluble. So copper 2 plus aqueous plus chloride aqueous. You have 2 chlorides. All give you, notice silver chloride's a solid, so you keep it intact. AgCl solid plus copper 2 plus aqueous plus 2NO3. 2NO3 aqueous. 2NO3 because we have 2 nitrates, right? So that is your total ionic equation. That is the result of breaking apart everything that is soluble and leaving intact anything that is not soluble or a gas. All right, so our net ionic equation, remember, to get to the net ionic equation, we're thinking, what are the ions that participate in the overall reaction? To figure that out, you cross out your spectator ions. Who are our spectator ions? They're anybody that shows up twice. We're specifically talking about the species, so you're looking for the exact same ion or element or whatnot on either side of the reaction. So you look at nitrate. Nitrate looks like it shows up here in the starting materials, and then nitrate also shows up in the products. So nitrate, you cross out. Nitrate's one of your spectators. What about chloride? You've got Cl minus here, but notice you don't have any Cl minus on the product side. You have chloride on the product side, but it's tied up with silver. Because it's tied up with silver, it doesn't show up twice. You don't think of it as showing up twice. In order to say that chloride shows up twice, you'd be specifically looking for Cl minus, and we don't see that. Same thing for silver. You don't see silver show up twice. Silver ions show up twice. You do see copper show up twice, though, right? You've got copper 2 plus ion and copper 2 plus ion that shows up. So the only thing that's left is the silver, the chlorine, the chloride, and then the silver chloride. So your net ionic is 2Ag plus aqueous plus 2Cl minus aqueous, giving you 2AgCl solid. 2AgCl solid. We can do one further thing to this. Balanced chemical equations should reflect the smallest whole number coefficients. So you look at this net ionic equation and you see that silver, chloride, and then silver chloride all have a 2 in front of them. You can simplify this. You can reduce that 2 to a 1, right? You could just get rid of the coefficients in front. And so your net ionic equation is just 1 silver ion plus 1 chloride going to 1 silver chloride. All right, so this is your total net ionic equation simplified. All right, so that's the net ionic equation for a precipitation reaction. Let's see about sodium chloride and potassium bromide. So you first want to write out the balanced equation, right? To start, just by swapping the ions. So sodium is going to pair up with bromine, NaBr. Potassium is going to pair up with chlorine or chloride, right? Those are your products. Consult your solubility rules, and you see that sodium bromide is soluble in water, as well as potassium chloride. When you have this kind of situation where the ions that are the products that you predict are both soluble compounds, again, soluble compounds are the aqueous ones, you have no reaction, right? So if you specify this kind of pairing with the ions, you want to write no reaction for your equation. You could also say if you don't want to write out the products, you could just say this as well. KBr, aqueous, goes to NR, no reaction. So you don't have to write out anything further than this. You don't have to write a total ionic, and you don't have to write a net ionic because there's not a reaction. All right, how about HCl and potassium sulfite? Okay, so if you go back and you look at that table of gas evolution reactions, one of the things that is included in there, is that sulfites generally result in the formation of gases. So this is an instance of where you look at your starting materials and you look to see, well, do I have sulfites or not? Because you have a sulfite, this is a sulfite, right? Sulfite is SO3 2-. We're going to be forming a gas in this reaction. So let's predict the products real quick. I'll show you how you can work through these things. So if you swap the ions out, you get KCl pairing up with potassium pairing up with chloride. That H is going to pair up with the sulfite to give you H2SO3. H2SO3. Now, what you got to do is recognize that this thing, H2SO3, will decompose into water and SO2. So H2SO3 actually becomes water plus SO2, right? If you balance it out, you can see there's 3 oxygen on either side and 2 hydrogen. So what I'm doing is I'm showing you the intermediate step. You don't have to show this intermediate step, but it's important to know that if you predict something like H2SO3, it actually is going to decompose into water. Your final reaction, though, should look like, your final balanced equation should look like HCl aqueous plus K2SO3 aqueous going to form KCl, which is going to be aqueous if you consult your solubility rules, plus H2O, which is going to be a liquid, plus SO2, which is a gas. It ends up being a gas. So this is your balanced equation. Just to start, doesn't include your total ionic or your net ionic. So you got your balanced equation. Let's do the total ionic equation. So total ionic equation. You're going to break apart HCl. So it's going to be H plus. Or actually, hold on a sec. I got a little far ahead of myself. We need to balance the equation. It's not balanced. There should be a 2 in front of KCl, and then there should be a 2 in front of the HCl, right, to give you something that's balanced overall. Now we're balanced. Why that's important is because it allows you to have a balanced net ionic and total ionic equation. Okay, so we break apart HCl. That means we've got 2H plus aqueous plus 2 chlorides, also aqueous. Potassium sulfite is going to be aqueous. K2, so 2 potassiums, aqueous, plus SO3, also aqueous, SO3 2-. That's going to give you 2 potassium, aqueous, plus chloride. Two chloride aqueuses, right? (2Cl) aqueous plus water is a molecule, SO2 is a molecule. So you just leave them. H2O liquid plus SO2 gas. that is your total ionic equation. All right. To get to our net ionic equation, let's cross out everything that shows up twice. Chloride shows up in the starting materials. It also shows up in the products. Excuse me. We cross out chloride. Potassium shows up in the starting materials. It also shows up in the products, potassium ion. So we cross that out. Notice H plus does not show up in both the products and the starting materials, and SO3 doesn't either, right? So our net ionic equation is going to be that 2H plus aqueous plus SO3 2 minus aqueous, giving us H2O liquid plus SO2 gas, right? That is our net ionic equation for a gas formation reaction. All right, folks, last but not least, this is an acid-base reaction. We've got HI, which is an acid, and we've got sodium hydroxide, which is a base. When you have an acid-base reaction like this, you're going to be making water and a salt, right? Because you're making water, you know you're going to have some kind of net ionic equation. So let's do this reaction. Let's write the balanced equation first. So the balanced equation, if you swap the pairs, that H is going to pair up with the OH to give you H2O. H2O is going to be a liquid. That I is going to pair up with sodium to give you sodium iodide. If you consult your solubility rules, you see that sodium iodide is aqueous. This guy is, of course, the water that you're forming in the acid-base reaction. This is the salt, right? The two that you get. HI is the acid, and NaOH is your base. Okay, so that's your balanced equation that you get. What about the total ionic equation? So your total ionic equation, remember, you want to break apart anything that's soluble. That's anything that is aqueous. So that means H plus aqueous plus iodide aqueous plus Na plus aqueous plus OH minus aqueous, right? That will give you leave water intact, liquid water, plus sodium iodine, or sodium aqueous plus iodide aqueous. All right. Then we cross out the spectator ions, which in this case end up being iodide and sodium. And our net ionic equation then is H plus aqueous plus OH minus aqueous, giving us water. And that is it. You know, the one thing I forgot to do is indicate the driving force, right? I didn't tell you the driving force. Remember, driving force for reactions are going to be solid formation, gas formation, or the formation of water. So the driving force for this guy is water formation. It's going to be water formation. The driving force, I'm just going to call it DF, for this reaction is water and gas formation. That is what propels this reaction forward. There is no driving force for this reaction, right? Because there is no reaction. The driving force for this reaction, your precipitation, is solid. Solid, which we also call precipitate formation. All right, and that is